graphical method. We're going to have a little bit of okay. So and then get these to the with 4y to have it in somewhere. Or yeah, that way round. 2 Pi. 2.3 was minus 1.2. And the second one, yeah, can in a minute, hang on. Well, the rearranging of the equation, is that not the answer you got, or?
Yeah, no, yeah, I done the first one.
And the second one, minus 2 and minus 3. X is minus 2, y is minus 3. The rearrangement of this first one, 1.4x minus 7.06 is equal to 3.2y. We can just straight away divide through by 3.2 there, so we can end up with y is equal to 1.4x over 3.2 minus 7.06 over 3.2. Yeah. This one, 2.1x minus 6.7y is equal to 12.87. Recommended route here is we got a negative y term, so let's add that to the other side and make it positive. So 2.1x is equal to 12.87 minus plus 6.7y. Then we subtract the 12.87 from the other side. So let's put our 6.7y on this side where we want it, and then say that's 2.1x minus 12.87, and then divide, and then lastly divide through by the 6.7. So we got y is 2.1x over 6.7 minus 12.87 over 6.7. And however I started off with them numbers and ended up with two just single decimal place numbers as answers, I don't know. Yeah, if you're doing the recommended route is to get it into y is equal to mx plus c linear form. In actual fact, as some of the other guys have asked me, you could probably type with this software, type in the function as given, and find the same answer. But part of the process you need to go through for the assignment question requires you to rearrange the equations. Okay. Well, you could do, but that's just going to draw the same lines over the top of the ones you already got there. So I need you to show me this process. So we're doing it this way. All right. I can see what you're saying. That would show if you rearranged the equation wrong, wouldn't it?
Yeah.
Is that what you mean? You're checking your rearrangement. Yes, I agree. Yeah. One good way to check a rearrangement is to imagine two easy values of x and y. Let's say 1 and 2, right? Calculate what the value is in your formula of the answer, and then do the same in your rearranged equation. Do you get the same result? Because if that's rearranged correctly, you should do, shouldn't you? Right? So, moving on to next page. An engineering example. Okay? And you're going to get some kind of engineering example in your assignments, by the way. In a system of pulleys, the effort E in joules, notice there's engineering units involved here, gentlemen, so you need to be aware of that, is related to the load L in newtons by the formula E is equal to AL plus B. In it. effort applied is 90 newtons, the effort applied is 22 joules. Using graphical methods, we're going to determine effort required to lift a load of 30 newtons and the load that can be lifted with an effort of 25 joules. The first step for you to do is formulate two simultaneous equations using the given data and arrange them in a linear form. So I'll leave you to do that for the 2 equal to something, because we got to find the first to do is formulate two equations, get a form where we could use graphical software to find the constants A and B. Right, gents, attention please. How do we formulate initially two simultaneous equations from that data? Put the data into the equation. So the first one, we've got an equation E, so we want 12 equals, so we'll write 40A because that's the way we usually write it, plus B. That's the first equation. And the second one, 22 is equal to 90A plus B. Second equation. The next step is to rearrange both of those so that they are in A is equal to and an mx plus c linear form. So again, right guys, what we got for these two equations rearranged? So our A is equal to something. Adam, put you on the spot. Equation 1, rearrange so it says A equals something. Am I right? Have you done it or not? No, exactly. My point precisely. I equals really? Where's the B gone?
No, you got that. It's minus y. It's minus y in the terms of y.
First of all, we've got to take B away, haven't we?
Yeah, but it's the answer.
40A is equal to 12 minus B. Agreed? Then divide by 40.
No, isn't it minus 40?
A is equal to, and we can make it minus B over 40 plus 12 over 40. Do you agree with that? Because now that's in. Remember what it is. The key I want you to do is in x is equal to mx plus c form. Yeah? Linear form. So we're going to substitute in the graphing software x for a. We're going to substitute that's you like it yapping, confusing me. Y is equal to mx plus c form. So that's what you should have. Do you agree or not? I've took b from both sides. I just changed the order here. Divide by 40. So that's the first one. The second one, we got 22, so we're going to, again, I'm going to subtract b. So 90a is minus b plus 22, and then divide through by 90. So we got a is equal to minus b over 90 plus 22 over 90. Correct. Yeah? Then now in standard linear form, the slope here being minus a 90th, and the slope there being minus a 40th. Then you enter them in the graph and get the value of the constants a and b. You're going to have to substitute y for a and x for b. Algorithms. Gentlemen, please. Division of logarithms and the laws of logs. Essentially, logs are just another way of manipulating numbers with an index, like powers. Okay, but there are a number of engineering topics that have relationships that are logarithmic in nature. For instance, the charging and discharging of a capacitor has a logarithmic relationship. Okay. So, in general, a logarithm is defined as follows. If you've got a number y that's equal to a to the x, then that number, the power x, is the log to the base a of y. So if we write 1000 is equal to 10 to the 3, and we all know that's true, right? Then the log to the base 10 of 1000 is 3. That's that index x. Okay? Now, if you study engineering, certainly if you study it here, you're going to come across two bases for logarithms only, really. One is the logs to the base 10, also known as common logarithms, and they're the log or LG function on your calculator. So the log to the base 10 of 100 is 2. If you do log 25, you'll get 1.398 to 4 significant figures. When we write these logs to the base 10 out, because they're common, the most commonly used base other than those to e, we generally drop the 10 and just assume if you don't put 10, if you don't put the base, it is a log to the base 10. Okay? What you'll also meet is logs to the base e, or natural logarithms, the ln function on your calculator. Designated function ln, and ln of 100 is 4.605. ln of 25 is 3.219. So, they're different results to natural logarithms. E, just for information, is what's called the exponential constant, and it's approximately equal to 2.7183. Okay? It is a special number, and you'll find out why. One reason why it's quite special when we look at differentiation and calculus in the last learning outcome of this module. But when it's a special function where its slope is equal to its value at any point. So that's the reason why that is special. I won't worry too much about it at the moment. Sure you won't. If we graph functions, logarithmic functions, the left-hand one is y is equal to the log base 10 of x, and the right-hand one is y is equal to the natural logarithm of x. The one thing to note about both of them is neither of them exist for values of x greater than, less than or equal to 0, sorry. So if they don't exist, you'll get an error on your calculator if you put the log of 0 or the log of a negative number in your calculator. Same with the natural logarithm. They don't exist for numbers equal to or less than 0. Alright? Inverse logs. If you're going to be able to manipulate equations that include logarithms, you need to know what the inverse operation is. So when we add something to both sides or subtract to both sides to move it around, or we know that square and square root are inverse of each other or opposite of each other, we need to know what the opposite of logarithmic functions are. That's often called finding the anti-log of that number. The anti-log of a log to the base 10 is 10 to the x. Okay? So the anti-log of 3 is 10 to the 3 is equal to 1,000. So if we got, we know the log of 1,000 is 3, so the anti-log of 1,000 out of 3 must be 1,000. Just a matter of being able to go backwards and forwards, and the anti-log of a log to the base e is e to the x. And the easiest way to remember is on your calculator, they are the shift functions on the two log keys. So if you look at your log key, you'll see that the shift function on that is 10 to the x. And if you look at your ln key, you'll see the shift function on there is e to the x. And I've put that little tip on there. And if you do that one, if you take the log of 20, okay, and then do shift log of the answer, it should go back to 20 again. Okay, so everybody happy what the two different logarithm functions we're going to meet are. And for the assignment, you're going to be involved with logs to the base 10 is what we're going to be using. That's if you want to get a merit, that is. Okay, so there are 3 laws of logarithms, gentlemen, that allow us to manipulate logarithmic functions. Can apply to any function regardless of base. There's a caveat in there. The logarithmic bases of those two numbers need to be the same. But these laws can be applied to natural logs or logs to the base 10 or 2 or 8 or whatever you're working with, as long as they are the same. The first law is that the log of a times b is equal to the log of a plus the log of b. So what that means is, if we wanted to multiply two numbers together, we could take the log of those two numbers, add them together, and then find the anti-log of the result, and we have multiplied those two numbers together. Yep. Believe me or not, do the log of 2 plus log of 6, and then do 10 to the power of the answer. And what should you get? What should you get? We're going to add the two logs together, Harry. And that's the same as multiplying the two numbers together. So what should your answer be? 12. So if you do log 2 plus log 6 equals, and then press shift log of the answer and equals, you should get 12.
What's the thing? The answer.
Because that's to find the anti-log, Lewis. Yeah? Another example there. The log of 3 plus the log of 4 is equal to the log of 3 times 4. What? Log of 2 plus the log of 6 is equal to that. Now find the anti-log of the answer. Press shift log answer equals. 12. You're fucking done now.
I didn't finish the brackets.
Yeah, you got to finish the brackets when you add them together. Look, log 2, right, plus log 6 equals, right, shift log answer equals 12. Right? Before the age of calculators, when I was a lad at school, we had books with tables of logarithms in, and that's what you'd use to multiply tricky numbers together. You use this law of logarithms. You found the log of both the numbers you wanted to multiply, added them together, and then went in the anti-log tables to find the answer. No, not particularly. They look like just thousands of numbers on pages, but you just look across all in lines and columns. I might have one. I'll see if I can find it. They also had sine and cosine tables in for doing your trigonometry as well. The second law is, gents, please, second law is that the log of A divided by B is equal to the log of A minus the log of B. Be careful with that one. It must be the log of the numerator take away the log of the denominator. You've got to get those two in the right order. With multiplication it doesn't matter. With subtraction it does. Okay? And then the last law is that if you've got the log of A to the n, that's equal to n times the log of A. And this all useful manipulations, as you're going to see in a minute. So you can actually use it to manipulate an equation. Alright? That's what we're going to do next week. Ain't done yet. So, what I want you to do now, okay, is have a go at them. Write the following as the logarithm of a single number.
Yeah.
Right, gents, let's take a look at these, shall we? The log of 2 plus the log of 3. How else could we write that? Log of 2 times 3. That's by law 1, which is also equal to log of 6. Yeah? This one, law 1, log of 3 times 5, log 15. This one, log of 3 times 4, equals log of 12. Ain't the log of one number though, is it? Not the final answer, is it? Look at this, right? Look at your question. That bit has added those two together to get the log of 12. Now we've got to take away from that result the log of 6. Yeah, which is equal to the log of 12 over 6. But you just told me, you didn't tell me how, did you? You told me that was a log of 12 over the log of 6. Not the log of 12 over 6. Right?
That's outrageous.
Sorry if I'm being pedantic, but that wasn't what you said, was it? Alright? Next one. Result of the first bit is log of 7 times 21. Log 147. We've got to take away from that the log of 49. So that's a log of 147 over 49 equals log 3. Yeah? Okay? And actually you can do these in one go. Here. That one, I could have put the log of 3 times 4 over 6 and done that all in one go. Same as that middle one. What about this one? How have we done that one? Number 5. Log 2 to the power 2. Is equal to the log of 4. And then we go plus log 3. Log of 12. And the last one, the answer is, final answer? No. Log of 500. V equals Ki to the n. So, just to finish off, making, and I've already given a couple of clues around the room, making n the subject of Ki to the n. Adam. Go on then. I want to know your method. So did you start where I suggested taking the log of the sides? Well, and just left the n where it is. Now you know you can't do that, don't you? Yeah. So what have you done really? Well, I already give you the tip. Take the log of both sides. So we write log of v is equal to the log of k I to the n in brackets. Yep. Now, this is two numbers multiplied together. K is a number and I to the n is a number. Yep. So, the two numbers multiplied together, we can split them by law 3 on the right hand side. So we apply law 3 to the right hand side. We can write log of v is equal to the log of I to the n plus the log of k. So now what can we do with the log of k? We remember what we're heading for. We want n on its own. So if we subtract the log of k from both sides, log of v minus the log of k is equal to the log of I to the power of n. What can we do with that side? Left hand side. By law 2 we could write that as log v over k brackets. Yeah, sorry, that's my writing, Karen. Is equal to log of I to the n. How can we get n out of that side? Law 3 on the right hand side. Apply law 3 to the right hand side. We've got log of v over k is equal to n times the log of I. Yeah, from third law. Yeah. Now can I get n on its own? Divide through by log I. So I'll write n on my favourite left hand side, and on this side I've got the log of v over k divided by the log of I.
Well done. Boom.
Boom!
Boom.
All using those laws to switch between and using different ways of writing the number to the end that you're trying to achieve. Alright? Algebra. What do the big A word. Need to be comfortable with it.